published on March 2019, and the title is the Riemann zeta function in short intervals. And this is a survey that Harper surveyed some recent work on the behavior of Riemann zeta on the critical line on short intervals of T. In this aspect, there are several conjectures. One of them, made by Rudolf Harry Keating, they say they wonder what is the maximum value, or what is the distribution of this. And these conjectures come from the people who want to study the maximum of Riemann zeta function on the critical line. Because Riemann zeta is a continuous function. Upon complex set, continuous function has maximum value. So people are asking how large the maximum of Riemann zeta be. And this function has a name. Actually, this function is called the shifted Riemann zeta function. This alpha is a function of this capital T, and it is called the shifted Riemann zeta function. The reason why people introduce such a function is in the need of understanding the maximum of Riemann zeta. For this aspect, this conjecture is about is introduced to guess to conjecture that maximum. And also here is an advertisement. My colleague PJ Wongjie, he and his colleague introduced this shifted Riemann zeta function for the study of the moment problem of Riemann zeta function. So this is not something like we're just lazy and for nothing to introduce it. No, it's for concrete purpose. So the Riemann zeta function, if there is a function here, this is called shifted Riemann zeta function. And in that article, Harper mentioned shifted Riemann zeta function. He also, this is a survey, and Harper written in a way like to give a unified point of view of those graduate mathematicians' work. In order to do so, Harper introduced some assumptions to the readers. He says if you accept this, if you accept that, then blah blah blah, their work is understandable through this context. The first assumption Harper made is, suppose you have a capital T, you fix that, you let capital T vary, and then this is the shifted Riemann zeta as introduced. The values of this function and this function, as you can see, this is, in here we have alpha 1, here we have alpha 2, so there are two different shifted Riemann zeta. They behave roughly the same when this shift is not so large. That's the first assumption. The second assumption is even more interesting. It says that the true shifted Riemann zeta, if the shift is large, then they behave roughly independently. Roughly the same is pretty much easy to understand, just maybe coincide everywhere or coincide almost everywhere or some other sense. But throughout this article, it seems that Harper didn't mention the meaning of this roughly the same very specifically. Also, this roughly
is alpha real or complex?
It is a real function. Yeah. And it has to set up. It is a function in capital T, and it has to satisfy certain growing condition. I will introduce it later. And also, throughout this article, Harper just say these two are assumptions, not proofs, not conjectures. So we're mathematicians, we prove things, we disprove things, but we seldom make assumptions. So this is actually something makes me curious. So I'd like to study the two assumptions, or say respond to Harper's two assumptions. I want to make it rigorous. What does that mean? Say roughly the same. In what sense, maybe? Or roughly independently, in what sense, maybe? So that's the whole motivation of this whole project. Alright, so let us begin from return from the beginning. So what is Riemann zeta function? So this guy is Riemann zeta function. And for real power greater than 1, you can define it like this way. And also, of course, it admits Euler product in this way. For real power greater than 0, it admits the integral representation. And if you denote Cs to be like this guy, then C is a completed Riemann zeta, and it has this property. And people have functional equations so that you can extend the Riemann zeta to the whole complex plane, except for the pole on 1. And the study of Riemann zeta arises in the study of prime number theorem. And this theorem follows from the non-vanishing result of Riemann zeta. And this is maybe the one of the most famous hypotheses or conjecture in mathematics. All the non-trivial zeros of zeta lies on half line. And since we are NTHU, I don't need to explain this anymore. Good. Okay. And just like my title suggested, log correlation. So it is expected that some of the probability is involved. So let's do some review of probability. Real analysis speaking, a probability space is a major space and its total major is 1. What is a random variable? Well, you can understand it as a measurable function. That's it. So random variable is just a measurable function. For probabilists, we care about the distribution of the function rather than the function itself. So this is an important thing to probabilists. We call it distribution function. Like we always use the word normal distribution. That distribution is in fact refers to this distribution function. Okay. Some people call it cumulative distribution function, CDF, but never mind, we just call it distribution function or distribution. In real analysis, the distribution of a measurable function is defined in this way. So here is a little bit discrepancy between the word distribution in probability and in analysis. So probability we consider less than or equal to. In analysis we consider greater than, but in the end they will be equivalent somehow. So it won't be so that important. But throughout this talk, by distribution, we meant this greater one. Okay. And also another standard shorthand. People are lazy, so usually people would like to suppress this little omega. So we denote this one simply capital X. Capital X is a random variable, is a real valued measurable function. Greater than little x, probability of that really means you collect all the little omega in capital omega such that this one is greater than this one. Okay, this is a standard shorthand. Okay. A little bit hardcore concept comes from now. We call convergence in distribution if the corresponding distribution functions converges. Okay. If you know functional analysis, in fact, convergence in distribution is just a weak star convergence. So from functional analysis point of view, we understand that we know that the concept of convergence in distribution is a pretty weak concept. Most of the time, we don't have anything we want. Okay, it's really weak. Okay. Something more. So speaking of normal distribution, if you're not a probabilist, it's okay just to remember this guy. This bell-shaped curve is normal distribution. If you want a little bit more hardcore, then you may remember this is the CDF of normal distribution. Okay, just like this. Now, this is the famous theorem in probability, central limit theorem. It says if you have an IID, independently identical distributed random variable whose mean and the variance with mean 0 and the variance 1, then you sum them up, divide it by square root of n, and you take n goes to infinity, then the distribution of this guy converges to the distribution of normal 0, 1. Okay. So now you may wonder why I mentioned all of this, because in 1946, the great Selberg proved this thing. If I have a Riemann zeta function, you consider it on the critical line, you take log. So it is a complex value function. And this guy, when little t goes to infinity, is approximately like a complex normal distribution. So just like this one, okay. But a complex. Okay. And this theorem is called, nowadays is called the Selberg central limit theorem because it goes to the normal distribution. Recently, or say after Selberg's original work in 2017, Maxime Roosevelt and Kalman Soundararajan, they gave a new proof of this classical theorem, Selberg central limit theorem. And the precise formulation is like this. Oh, by the way, in Selberg's work, he did for the whole complex function, but for Roosevelt, Soundararajan, their method is for real part of zeta only. And they said in their work, this paper, that their work is much better to do for real part, and it's harder if one applies their work to imaginary part. Okay, so there are some compensation. So they only do for real part, but this is enough for us. So it says you fix the little v, and also you fix capital T initially. So you have an interval t to 2t, and this is Lebesgue measure. Now you pick up some t randomly over this interval. You plug in your Riemann zeta. After taking after taking absolute value, then log, you divide it by this magical quantity half log capital T. You compute that outcome to see if that T will make this whole thing greater than or equal to your little v, say 1 maybe. If it is so, you collect them inside. If it is not, you throw it away. You do this, you divide it by little t, so you have a measure, you have a quotient, a fraction in t. Then you let that capital T goes to infinity. The left hand side will goes to this, and this is the density function of normal random variable. So that's why it is called the central limit theorem, because on the one hand we have a distribution of something, on the other hand this distribution converges to a normal distribution. Okay, and I'm not sure if we have a probabilist. Some probabilists formulated this theorem in this way. Simply says this one converges normal 0, 1, and this is a uniform distribution on 0, 1. Okay. But if you're an analyst, this one is okay, in fact. And throughout my talk, I will be using this form instead of this form. Okay. Alright, so now let's see how we respond to Harper's assumption. And what is Harper's assumption? Assumption 1, you let capital T fix large, and you consider interval capital T to 2t. You let little t varies in between, and you observe this function absolute value of zeta half plus it and plus I alpha 1. Of course, alpha 1 and alpha 2 are given, and then they are roughly the same. And this is our response to this assumption. This roughly the same actually means you consider the difference between the two functions, but you need to normalize it. You need to take log and divide it by this magical quantity. You consider the difference. You put any t inside, and the difference is arbitrarily small, and those t such that this difference is arbitrarily small will tend to 1, which means that means the roughly the same is really rough the same. Okay, for any fixed t, it's not 1, but you let t goes to infinity, ultimately it will goes to 1, and they will be very, very close. Okay, and just like we said, alpha are real value function, and it satisfies this growing condition. The absolute value of alpha has to be less than or equal to half of that capital T. Furthermore, you can see the conditions are different. In Harper's work, he only assumed that alpha 1 minus alpha 2 is less than or equal to 1 over log t. But here, we use this condition. We consider the reciprocal of the alpha 1 minus alpha 2, and then we take log. But in fact, a little work shows that this one is, a little work shows that this one is equivalent to this one without this little r log t. Okay. We put this little r log t because our machinery allows us to do so. This is the broadest or weakest condition we can have. Okay. But the key idea is still, if the shifts are small, then they are the same. Okay. This is the response to assumption 2. Assumption 2 says if the shifts are large, then they are independent. Okay. Now, what does that independent mean? That means you consider a pair of normal distribution, by so-called bivariate normal distribution. We can understood it as just a 2D normal distribution. Okay. And then you put your normalized Riemann zeta here. You use comma to make it as a vector. Now I'm saying this vector will converge to a bivariate normal random variable in the sense of distribution. And moreover, we can calculate the correlation between these two functions, and the correlation of these two goes to 0. So it will go to an independent bivariate normal distribution. And as you can see, our condition is different from Harper's original one. We will explain it in 2 slides later. Okay. So now, some more probability course. If we have two standard normal distribution and we put them as a vector naively, you can check textbook. You won't automatically get a 2-dimensional normal unless they are independent. Okay. But here, the tricky part in this work is that for this individual one, this one goes to a normal, this one goes to another normal. So these two limiting distributions are given a priori. We know them, but we don't know if they are independent or not. So simply putting them together won't give us a 2-dimensional normal distribution. So this theorem actually requires some work. Okay. And the normal distribution, that bell-shaped curve, that is 1D normal. And if you remember, the Fourier transform or characteristic function of 1D normal is this, then it's easy to define a 2D normal to be a random variable having characteristic function or Fourier transform in this way. Okay, this is how we define a 2D normal. But roughly speaking, you can imagine just you put a normal on one component, another normal on the other component. But keep in mind, it won't always work. Okay. All right. So now let's review what we have done. So we have successfully responded Harper's assumption 1. The meaning of this roughly the same is actually means the difference between you take this log, take log divided by half log t. The difference is arbitrarily small, and the measure of that difference for being arbitrarily small is 1. And this is Harper's condition. This is ours condition. Harper says roughly independently. In our notation, that means these two, you put it as by a vector. This vector goes to a bivariate normal, and that limiting random variable, that bivariate normal is independent. Okay. And notice that this is Harper's condition, this is ours condition. Okay. Now this is the interesting part in Harper's paper. So Harper used these two assumptions in the beginning, and then in the very few pages, all of a sudden he said himself, it seems that this condition is not enough to guarantee the independence. And in Chinese, 第一次我在读的时候，我觉得 Harper 你在干嘛？为什么打自己脸？你前面这样说他会 independent， 然后后面说不会。Moreover, Harper doesn't just say seems. He provided a concrete example. He says, you consider example like this, you consider a series like that. If you only just have this, then by some standard calculation, he also showed the calculation. it seems that the correlation is not zero, therefore these two are not independent random variables. Okay. And to me and to my co-author Peng Jie, we think like, oh my god, what are you doing, Harper? You contradict yourself. Actually, this is another motivation for our project. Try to understand what does Harper mean by this, because apparently he has a contradiction. We want to make the condition for being like the same, being independent more clearly. And it turns out the benefit of using this violate assumption is clear when we consider something like this. I mean, using the blue one is not sufficient. Roughly, at a glance, it seems exhausted all the possibility, but according to Harper's calculation, it seems that this is not sufficient. We should use a finer characterization between the shifts. And it turns out this is our finding. Suppose we begin from here. You consider 1 over this, then you have 1 over this greater than log of 1 over log t. Taking log, you have this. Adding this little also is okay. But if we begin from here, you will have this one is less than or equal to log t. Like this. This is something in original, this blue one, but not captured by our violet one. And we believe it is this one that makes correlation. Okay, it is this one that make this blue condition not sufficient, not enough, and this is our guessing. And this is our theorem. So if you consider the shifts not so large, not so small, they are growing with a certain nice rate, exactly like this, for some number, real number in between 0 and 1, then this Riemann zeta, log zeta, and this log zeta, once again you put them as a vector, and this vector will converge to a bivariate normal, but the limiting bivariate normal will have a correlation. And amazingly, that correlation of the limiting bivariate normal is given or is exactly this quantity. Okay. Let me say it again in Chinese maybe. 所以就是你考虑我们这个 shift， 刚才说的这个 shift 很大的时候，你收敛过去就会是 independent。你 shift 很小，收敛过去是两个几乎一样的。那你这个 shift 的 growing 假如是刚刚好在一个很奇怪的地方的话，那它这边你把它放成一个向量，它收敛过去就会是一个一样是 normal， 可是今天它那个 normal 那两个 normal random variable 它会有 correlation， 这个就是 Harper 他这边说好像不充分的原因，因为它的这个蓝色的 condition 没有办法 characterize 到像这一个东西，可这个东西会给你 correlation， 然后 surprisingly 这一个数字刚刚好就是你 limiting variable limiting distribution 的那个 correlation， 非常非常的神奇。对，我不知道发生什么事，那我算出来的时候是真的满身鸡皮疙瘩。OK， alright. So now let's do a brief summarize. We set Cij to be 1 if this condition is true, if this growing is greater than log t. Let me write this on the board. allow me to introduce our main theorem. So now suppose you have a sequence of shifts, and suppose they satisfy either this condition, namely the growing 1 over the difference between alpha 1 and alpha 2, you take log. If it's either larger than log t plus little of log t, or it equals to some constant times a multiple of log t. Moreover, you assume this magical condition. In fact, this means if you list those Cij as a matrix, this condition ensures that your matrix is positive definite. So furthermore, we assume those Cij forms a positive definite matrix. Then there exists an n-variate, namely n component, and each component is normal random variable, with mean 0, and the covariance matrix of this distribution is exactly the matrix you given, and this C12, C13 is exactly the distance, the growing condition of alpha 1 and alpha 2, and alpha 1 and alpha 3, so on and so forth. So suppose we have such a nice property, then this normalized Riemann zeta, normalized shifted Riemann zeta, will goes to this n-variate normal in distribution. Moreover, the correlation will converge to the corresponding correlations. Okay, looks sophisticated. And here I want to remind us, for probability people, if you have a random variable converges in distribution to another random variable, this won't mean that the corresponding correlation will converge. Okay, because correlation is like square in the expectation, but convergence in distribution can think is even weaker than almost surely converge. So dominant convergence theorem tells us it won't be true if you don't add certain more conditions on there. Okay. So this is furthermore, this is not for free. We need to prove it, add some more condition. Okay. Right, so this is our theorem. I remember we initiate this whole project in like October or September of 2022. By the end of that year, we finished this theorem, and we were happy. And it is me who suggested to send email to Harper, saying, Professor Harper, it seems that we get a nice response to your assumption in your article on seminar of Bourbaki. Actually, we didn't expect Harper would reply, but within a week, Harper did. I get email, that was a morning, and reply from Adam Harper. He says, Dear Bohan-Xun and Peng Jae-wong, thank you for your email. Unfortunately. And I was, unfortunately, it seems that at least the work you said on your title has been proved by Bogart in 2009. And we were like, oh my God, how can this happen? None of the work cited Bogart's work, but anyway. So in fact, this is Bogart's theorem published in 2010. Okay, we duplicate Bogart's work. And my colleague in UC, he said, Bogart is a decent mathematician. Anyone can duplicate Bogart's work is nice. You should be proud of yourself, young man. And he said, I reproved von Neumann's work, and I'm still proud of that. So, okay. But we want to apologize. First, our method, the method used by Bogart and the method used by us are totally different. Bogart's work is based on Selberg's original work. It requires a sophisticated zero density estimate. But our work depends on Roosevelt and Sundararajan's work. That work appears on 2017, later than Bogart's work. Moreover, this is the topic of Bogart's paper, mesoscopic fluctuation for zeta zeros. When we finish our work, we use keywords like central limit theorem, correlation, try to search, but nothing coincides or nothing show up. Most importantly, we think we're doing a number theory, so all the journal we checked are number theory paper. This one, look at its name, probability theory. So it's a very, very decent probability journal. So we totally forgot this work. We cannot figure it out. We cannot find it out. And moreover, it's even worse. So anyway, we were informed by Harper that our work for shifted zeta was proved by Bogart. Bogart used Selberg's method, and we use Roosevelt, Sundararajan. So like, we use their work, so we use this one to do our search. Bogart's work is prior than this one, so of course we cannot find Bogart's work. So that's our apology. Alright, we were a little bit frustrated, so we pause and look back to see what we have done. And we think about, oh yeah, we did a work on JTMB, and we did something similar to this shifted Riemann zeta, but what we done was Dirichlet L functions without any shifting. And this is one of the main theorem of our previous work. Suppose chi1 and chi2 are distinct primitive Dirichlet characters, and then there exists a bivariate normal with mean 0 and the variance I2, such that this vector, now you put Dirichlet character, goes to this bivariate normal. So now we think maybe we can do, because Riemann zeta has been done, so the next generalization is Dirichlet L function. So now we just do it for Dirichlet L function. Plus we have some experiences. So starting from the December of 2022, and we spent almost 3 months to revise our work. So finally we finished this, I think it's by April of 2023. So now let's rethink about what we have so far. So first, we know if we have shift, then shift create correlation. So if shifts are large, then they are independent. If shifts are small, they are same. If in the middle, then they are correlated. And according to our previous work, different Dirichlet characters automatically gives you independent. So now, how about we put them together? We consider shifted Dirichlet L function with different Dirichlet character. Would that have any dependence? Who wins? What is the probabilistic behavior of this one? You have different Dirichlet character, you have different shifts. The short answer is characters wins. Namely, as long as the character are different, no matter how close your alpha 1 and alpha 2 is, they will be automatically independent. Pretty amazing. Okay, so now this is, okay, before I introduce my theorem on Dirichlet L function, let us recall what is Dirichlet L function. So you consider let Q be fixed and integer, then Dirichlet character mod Q is a homomorphism from Q mod QZ to C, of course without 0, I think. You can extend this by this way. The Dirichlet L function attached to this chi is this guy. You replace the 1 in Riemann zeta by chi, and of course it admits this Euler product. And if you consider this principal character, it reduces to Riemann zeta. So yeah, they are related relatives. Similar to Riemann zeta, you can have a functional equation of Dirichlet L function. And the study of Dirichlet L function arises in this theorem. And in this is actually not the way I learned this theorem. I learned this in 赖恒龙老师的那个基础数论。他那时候有讲一个很漂亮的定理，他就说，假设你的首项跟公差是互质的，则你的那个等差数列里面就有无穷多个指数。然后赖老师来说，哦，这个东西我们现在证不了，就先讲给你们知道而已。对，我后来才知道，那个东西写出来就是这样子的东西。Okay, and this is a quantitative expression. All right. So Silber in 1946 proved log zeta, and then in almost same year, in different paper, he proved that his Silber's central limit theorem holds for Dirichlet L function. In fact, in Silber's original work, his central limit theorem holds for L functions in Silber class. Okay, if it satisfies certain nice property, then you always have this central limit theorem. And in 2019, we use Roosevelt and Sundararajan's method prove the real part of the Dirichlet L function is approximately normal. Okay. So now with the Dirichlet L function being introduced, now we can introduce the main theorem of this project. Is pretty complicated because now we have one more parameter. It captures if your Dirichlet character are different or not. We set this delta ij to be 1 if their product is 1. If their product is a principal character, 0 otherwise. And once again, you assume this matrix given by this delta ij and the cij to be a positive definite, or I have 0 here. Never mind, you can ignore this. This is a typo. Okay. Positive definite is easier to understand. If you have a positive definite matrix, then your log, okay, I should write this out. So this stuff looks very scaring. It's actually log of Dirichlet L function half plus I t plus alpha j comma chi j absolute value divided by this magical number half log t capital T. So each of this individual is one of this guy. So now you consider have capital N, so it's a huge long vector, and this huge long vector converges to an unvariate normal distribution. And we can also duplicate our previous work for Riemann zeta. We can also have this corresponding correlation converges to this one. All right. So now enough showing off. Let's talk about the method. Yeah, I have 20 minutes. So the ingredient of our proof is, first, we use Roosevelt-Sundararajan method to establish central limit theorem for one individual, this kind of stuff. So for an individual, we have converges to normal. And then we use existence theorem for multivariate normal distribution. That is to say, for a given vector u and in appropriate dimension, and a positive definite matrix K, there always exists a multivariate normal distribution with this u as your mean, and the covariance matrix is the given K. So the way we prove it is because they are all mean 0, so mean 0, and we use this Cij and that delta ij a priori given. We require them to be positive definite, and then we use this existence theorem. So there exists such a nice unvariate normal distribution. And the next thing is how to show this converge, okay, as a vector. And once again, if you have random variables, individually they converge. It doesn't mean if you put them as a vector and this vector converges to that vector. Wrong. OK. 小小的几率课时间。今天假如你有一个 random variable， 它 converge in distribution 到某个 random variable， 单单只是把它放成这样向量的形式，然后你要想说这个向量收敛到那个向量，这是不对的，没有那么简单。那你要怎么证明 how to prove the convergence of vector forms in probability distribution? One usually use this so-called Cramer-Wall device. Namely, you have to consider its linear combination. If the linear combination converges to this linear combination for any real A, and then you can say that this vector converges to this vector. Okay. So the tedious part of our work is individually we have this log L converges to some normal. In order to show they jointly converge, we have to show the linear combination of this guy converges to a linear combination of some normal guy. Okay. And that's the tedious part of our work. Also, we use some nice property of joint normal. That is, if correlation 0, then independent. This is not true in general. And if correlation is 1, then they have this linear property. Okay. So sum of probability is really used. Alright, so now for number theories, Roosevelt-Sandaraja method. So this method is pretty nice actually, pretty systematical. In their original paper, it consists of only 4 propositions. And each proposition is very clear why we need to do this, why we need to do that. But in short, the heart of that proof is you first, you want to truncate this log of a Dirichlet function into this nice finite sum. And because we consider real part, so we consider this real part. And this is a von Mangold function. And this is a finite sum. This capital X is a nice parameter, but fixed initially, and then we will let this X goes to infinity. We do this truncation, but from probability point of view, we want to show that those two, this distribution, the distribution of this guy converges the distribution of this guy. So this truncation has to be delicate. In probability, there is a theorem. Its nickname is called convergence together lemma, and its formal name is this Slutsky theorem. In short, it tells us convergence in distribution is really weak. If you have one thing converges to A in distribution and Bn converges to B in distribution, you add them together, you won't have this one converges to the sum in distribution. You have to have at least one of them in a stronger mode of convergence, like convergence in probability. And that is the delicate part of this truncation. Okay. If you truncate this to this, and then the strategy is to show that by moments method, you consider this integral from t to 2t divided by t and to the k, of course. This one equals to 2k double factorial, and that is the moment of normal random variable. So you use that, and in this proof, we need to show, it can be shown that the main contribution to this moment are all from prime numbers. So in fact, this looks maybe hard, but in fact, all the contributions are prime numbers. So then that would reduce to sum of 1 over p, and the p is less than or equal to x. That would be log log x. That's why log log t something appears everywhere. And when we do our shifted Dirichlet function, we need to modify an estimate by Trendy in QJM. Originally, that lemma was Trendy only needs a big O result. So in there, he just used greater than or equal to bound some quantity. But here, what we need is a precise equal to something plus some other error. So we need to modify her work, I believe it's her, modify her work to get a precise equal sign. And this is not, again, tedious because we need to track every detail in his proof, in her proof. Okay. In short, because we want to consider the convergence of vector, we have to consider linear combination of Dirichlet L functions. And the so-called linear combination involves addition, right? But their method, Rossiville-Sandaraja method, is of multiplicative nature. You maybe heard multiplicative number theory. Their work is indeed multiplicative nature, but on the contrary, we need to add something, so some more additional structure is involved. That makes the whole calculation very tedious. Okay. Alright, so such a linear combination approach comes from Cramer-Wald device. And so if we want to consider the joint distribution of L function, we simply consider the linear combination of the L functions. Okay. And such an approach has been adapted by my colleague P.J. Wong， 就是彭杰啦。他最近有一篇文章在考虑这个，其实这些字我都不太认得。Central value or an order of Sharp group of quadratic twist on elliptic curve. Okay, this is a work he's preparing, and he will upload this to archive this week. So if anyone is interested in, email him. Okay, I'm here to do the commercial. Okay. 好，然后这个。Alright, so we have Riemann zeta, that is a duplicate of the work of Bogar. We have Dirichlet, which is good. And one day, it is about like 3 or 4 p.m. Eastern time, I got a call from PJ. He was in Taiwan now, so that is 3 or 4 a.m. in the morning, very morning. He called me. He said, hey, it seems our work can be generalized to Dedekind zeta function because of this factorization. And I said, oh my god, it's super early. Alright, so I have to show, I've displayed this direct application. So, to me, it looks like if the extension is nice, then we can define Dedekind zeta function, and such a function admits this factorization product. Well, college students, we know if we take log, we can make product addition, right? So addition, this is Riemann zeta, this is Dirichlet L function. We divide it by square root of half log t. So now, by my previous slides, this one converges to normal 0, 1. This one converges to normal 0, 1. And in fact, these two behaves like independent normal random variable. So n01, n01, sum together, you have n02. Analogously, you can consider a sequence of Dedekind zeta function. Once again, you put them as a vector. You consider the limiting behavior of such a vector. You copy the previous work, you get this theorem. So this is a very broad. I only show you the covariance matrix, but actually a statement holds. Namely, if you have nice requirement on the shifts and also on the Now what? Yeah. This discriminant extension, and if they satisfy some nice positive definite condition, then that string of vector converges to a multivariate normal vector whose mean is 0, covariance becomes this. And this capital delta captures the corresponding Dirichlet character, and this Cij is once again a shift. And now you can see that there is a slightly difference between this one and the original Dirichlet L function. And that has some probabilistic meaning. Okay, but never mind. The probabilistic meaning is you have normal 0, 1 plus normal 0, 1, so we have normal 0, 2. This. But this is one of the direct application of two-Dedekind zeta function from our work. I think it's about time, so thank you.
So, any questions or comments?
Hi. I would like to ask about why we care about the probability distribution when the time tends to infinity.
Oh, this is an excellent question. I can answer this in several aspects. First, traditionally, because this is done by Silver, so whatever Silver care about, we care about.
Okay.
That's one reason. Another reason is, I don't know why, but recently those great mathematicians, including Adam Harper, they kind of using, including Harper himself. This guy worked on random matrix. This guy is a probabilist, and this guy used probability machinery to do number theory. So it seems that recently more and more people using probability point of view to do number theory, and from what's distinct from probability and analysis is distribution. So in general, analysis they care about the behavior of function itself, but the probabilist we only care about the distribution of that function. So we only care about, instead of caring about the behavior of zeta itself, we care about this thing, what we call the distribution. And if we consider in this way, then the whole probabilistic machinery can be come in and gives us more, information, we believe. Because, for instance, if you want to study the maximum value of Riemann zeta, you can study it directly. But on the other hand, you can ask how many t such that this Riemann zeta can exceed, say, 3. If that t is very huge amount of t, then you may guess that 3 is not the maximum value of zeta. Because maximum means you have only small portion, you can go exceed that quantity. So using this point of view, it also can be helpful for us to obtain more and more properties of Riemann zeta function and solve other Dirichlet L functions, solve other L functions. That's my 2 answers. Yes.
Thank you.
So, any other questions? Crystal.
So is this kind of distribution related to any property of prime numbers?
Oh. For Riemann zeta, I am not 100% sure, but I can provide 2 answers. For my result, everything will like this one. Everything will break down to the sum of this. some parameter in T, let's just say capital T. So this is one relation of relating to prime number because everything breaks down to this sum. The other is from zeta function, I'm not sure, but for like say little omega, the prime counting, prime divisor counting function, we also have some probabilistic theorems regarding that. So if we study that function, then maybe we can have more knowledge regarding prime numbers. So that's my answer. Maybe not from Riemann zeta, but for another function, if we use probabilistic approach, then maybe we can have some more understanding of prime numbers.
So here you use the known properties of prime number to establish something.
Yes.
But you also said that it can lead to some unknown properties of prime number.
Unknown properties. Oh, then I'm afraid that, to the best of my knowledge, I don't know. Maybe not.
So the other question is this seems that suppose we consider the distribution of value of the derivative of Riemann zeta function along the critical line. Is that somehow related to your problem?
The derivative of Riemann zeta, I have to admit I haven't think in that way, not yet. But so far what I do know is there are some people also studying the maximum value of Riemann zeta, and which leads them to study the distribution of derivative of Riemann zeta. But to my project, I'm not sure. Maybe not.
Because what you said is that in a relatively small interval, you essentially can have a lot of random values. So that must say something about the derivative.
Yes, but currently not in my mind, not immediately. So I don't know. I'm sorry.
So I have two questions. My first question is regarding, your motivation comes from two assumptions of Harper.
Yes.
So I was wondering, in Harper's seminar paper, Baki seminar paper, what's the conclusion after the two assumptions?
Oh, actually, the purpose of those assumptions is to introduce their studies. So the conclusion is, okay, you can use this unified point of view, then you can understand their method, their result in this unified way. But in the very, very last few paragraphs, Harper also mentioned it seems that this is not enough to ensure independence, and he did some calculation and just leave it there.
Okay, I see. So my second question is about, here there are some conditions of C, right, for your result.
Yes.
Could you please clarify, for what kind of C is for? It is independent, and for what kind of C it is?
Sure.
Yeah.
So, roughly speaking, if your C is 1, then that's independent.
Okay.
Oh, sorry, no. If your C is 1, then that means they are very close. So they will be roughly the same. If your C is 0, then they will be very far away. So that would be independent. If your C is in between 0 and 1, then they will have correlation.
Okay.
Yeah.
So suppose in general you have a symmetric matrix which is indefinite, then the negative eigenspace must be uncorrelated with the rest.
Oh.
Is that right?
If you're asking the negative correlation, the negative eigenvalues
of course the minimum correlation is 0. So I'm asking about the negative eigenspace.
Sorry, I am not sure about the answer. Yeah. So I don't know. Sorry.
Okay, so if there is no further question, let's thank for speaker again.还没签到，同学记得签到。